Hey, hello guys, a very happy morning to every one of you. Guys, now we are just going to see the next thing in the production engineering, okay? Because in the before thing, I just completely discussed about the theory. So in this, it means from here onwards, we will just have a little bit of problem discussion and a little bit of extra things, okay? I think you can understand. So let us get started. So before I just explain, okay, a lot of these things, okay, that's a good thing, okay? So with having 2 minutes of revision, I'll just come up again, okay? Just for okay, then I think so perfect. So okay, so type of meshing I just told to you, which means orthogonal and oblique, okay? So orthogonal is only 2-dimensional and oblique means 3-dimensional. So okay, these are the extra things I just told you, because suppose if I just want, I'll just zoom a little bit. Now I think so you can see. So you can see cutting edge is perpendicular orthogonal, but cutting edge inclined is it's oblique, okay? So cutting edge is wider, you can see wider than the which extends beyond the workpiece, and also width of the workpiece is much greater than the depth of the cut, okay? The cutting edge may or may not be wider than the workpiece width, okay? Then you can see in orthogonal, the chips generated flows in the rake face of the tool with the chip velocity is perpendicular, okay, to the cutting edge. But here it is been inclined, so it will just go in another angle. So you can see cutting force only 2-dimension, okay, 2 angles. So but here in this cutting force is in 3 direction, okay? You can see orthogonal cutting is 2 life is less, but in oblique 2 life is more, okay? Speed, feed, depth of cut I just told you, okay? Feed is just a simple thing, okay? Feed means it just feed, everything is given as mm per revolution, okay? Mm per revolution. So depth of cut is this one, it means entire d1 minus d2 divided by 2, okay? Because we are just taking one side. Speed I think so, it means as we are just moving, that's speed, okay? I think so you can understand v equal to pi dn divided by 60 meter per second, okay? So I think so you can understand n is number of revolution, okay? Okay, so this thing is okay, and positive rectangle, negative rectangle I just told you, okay? That's also perfect. So for single point, multi point, okay? Back rectangle, side rectangle, okay? Okay guys, then let us start. So it means it means 100 to 100% I won't tell, but I'll just explain the problems, so you will have a clear cut good understanding, okay? So orthogonal rectangle, it means I just told to you before why the orthogonal rectangle is used, because each and everything tool reference system is there and the machine reference system is there. For orthogonal rectangle we need a force analysis, okay? For the force analysis only we are just converting the tool reference system, it means American Standard Association, into orthogonal rake system, okay? Why this is being used? Because of the force analysis, okay? I think so. Inclination, it means orthogonal rectangle. This one end relief angle, it means side cutting edge angle, side end relief angle, and end cutting edge angle, and principal angle, and external radius, okay? Okay, I think so you can understand. So just a simple thing, okay? So you can see whenever lambda is 90, it means principal cutting edge is 90. So like this it will be, this is side cutting edge, this is the end cutting edge angle, and this is side cutting edge angle, okay? So I think so you can, so this is lambda, okay? Just a simple thing, okay? So while you just make a summation of this, it will come according to the angle, okay? So this was the exciting way. So you can see in a single point cutting tool, the side rake angle and the orthogonal rake angle are equal, okay? So side rake angle and orthogonal angle is been equal, okay? So theta is the principal cutting edge in line, okay? The chip flows in a orthogonal when the value of principal cutting edge angle is 90 degree, okay? Just a simple thing guys, okay? I think so you can understand. How to, okay? So suppose you can see if lambda equal to 90 degree, so side rake angle is equal to orthogonal rake angle, okay? So if inclination angle is equal to 0, you can see orthogonal, it means normal rake angle equal to orthogonal rake angle, okay? Suppose if I equal to 0 and lambda equal to 90 degree, means side angle means side, I think so, side rake angle, orthogonal rake angle, and back rake angle, sorry, and normal rake angle is all are similar, okay? So next one I think so you don't know about this one, okay? let us see this one, the shear angle. I think so you don't know about shear angles. How? So R is considered, so T by TC, okay. T by TC is also much important, and LC, length of chip divided by length of that cut, equal to VC, it means velocity of the chip divided by velocity, so equal to sine of shear angle divided by cos of shear angle minus of alpha, okay. This is shear angle minus of this one alpha, okay. Also is rake angle, okay. So equal to 1 by half h, okay. So 1 by h is just inverse, okay. It means R equal to 1 by half h, okay. So this is h is h equal to 1 by half r, okay. H is generally inverse of the chip ratio or chip reduction factor, okay, or chip compression. Anyways you can just take, okay. That's our issue, okay. So you can see whenever alpha, suppose this is the condition, if alpha is equal to 0, how the condition will be existing, okay. So for this one it's not generally here, but you can just go for it. So you can see during orthogonal cutting, that's one of the important thing that I just want to where it went, I literally don't know. So okay, anyways, okay, let us go. So you can see this one. So during orthogonal cutting, it is I think get 2001, okay. During orthogonal cutting, so you can see rake angle given, alpha is given, and chip thickness ratio R is given, okay. So first one, rake angle alpha 10 degree and R is 0.4. So they are asking the shear angle. So what I just formula in the before class, tan theta equal to R of cos alpha divided by 1 minus of R of sin alpha, okay. So you can see if theta, how you can just find. So theta means just tan theta equal to R is how much, 0.4 cos of 10 degree, okay, divided by 1 minus of 0.4 sin of 10 degree. So just calculate, you will come and answer. So pi equal to tan inverse of certain value, okay. That's it. So in the calculator you can easily do it, okay. I think so you can understand. So you can just go for the next question. About this one, okay. So that I can, you can see. So chip thickness under orthogonal machining, you can see uncut thickness, okay. What I just told, R equal to T by TC equal to, okay, LC by L and VC by V equal to 1 by half h, or R of sin, R of sin will not come, sin will be cos of minus alpha, okay. Okay, I think so you can understand. So T is just a normal thickness, okay, and TC is chip thickness ratio, okay. It means R equal to, you can see depth of cut uncut, okay, uncut chip thickness, so 0.8. So this T is uncut chip thickness, okay. How to say means it's like a depth of cut only, okay guys. How to say means let us suppose like this is there, okay. So I am just taking this depth of cut, okay, like this. So okay, this is the depth of cut, okay. So you can see I just placed it here, okay. You can see this is 0.81 mm. I just placed here, but still the chip did not come outside, okay. So if the chip comes outside, means due to thermal expansion also it just expands, okay. Due to thermal expansion or due to kind of the which you need to say the one thermal expansion, and second thing is what is the thing, due to the surface tension, yes, surface tension also this starts to curl, okay. So after the chip comes out it tends to be 1.8 mm, okay. So it will be 1.81 mm. So just make a cancel and we'll get a certain value of R, okay. So after calculating the value of, you can see rake angle is given, so tan pi equal to R of sin alpha divided by 1 minus of R of, where I am just doing, so cos alpha divided by R of sin alpha, okay. Just calculate and put the value equal to tan inverse certain value, okay. That's it, okay. I think so you can understand, just a simple thing question, okay. So you can go for this one. So you can see orthogonal rake, okay. So you can see here the single point cutting tool with the orthogonal rake angle, okay, not a normal angle. You can see here it is given rake angle, okay, but here it is given orthogonal rake angle. So each and everything is different, okay, under orthogonal machining condition, okay. Orthogonal machining condition, the depth of cut, okay, is said to be, depth of cut is T equal to 0.9 mm, and the chip thickness ratio is chip thickness is TC equal to 1.8 mm. So I'll get the value of shear, okay. So in this where is that formula, there is one 3 formula that is so much important to you. Wait, I'll just check it because since my note is missing, I couldn't find it out. So that's why the problem is there. So that's 3 is most important number. So I think so you can see this one. So you can see this one is also so much important, guys, because sometimes they may give any kind of different thing also. So why I'm just telling this is 3 important formula. So I'll just write in a black pen. T equal to D, okay. Thickness equal to depth of cut, okay. Depth of cut. So it is orthogonal metal cutting, okay. Orthogonal metal cutting. If T equal to F of sin alpha, okay. This is for turning. So sometimes in the question they won't give the thickness. It means depth of cut they won't give, but they will give feed. It is mm per revolution. Sometimes they will give, and sin of 40 degree, 50 degree principal cutting edge angle they will give feed as well as the sin 40. So due to that we have to take the depth of cut like this. Okay, this is for only for turning. So if T if you are given feed, it means feed into sin of 90 degree. This is orthogonal turning. Okay, orthogonal turning. Orthogonal means just like this. Okay. Like this. So orthogonal turning for this, okay. F of sin 90 degree, okay. This is orthogonal turning. So this is the 3 most important formula that you just want to remember in your mind, okay. So you can see here orthogonal machining condition. So this one, okay, orthogonal metal cutting. So same orthogonal machining, okay. It's not orthogonal turning. So you can just make sure how to calculate tan of pi equal to r of cos alpha divided by 1 minus of r of sin alpha, okay. That's it. Okay, by this you can easily calculate. So you can just go for this one. So you can see orthogonal turning, okay. So where is feed the whether they have just given, okay, they haven't given, wait, uncut chip thickness is 0.5 mm and normal chip thickness is 1.5, okay, then it's a fine thing, okay. So but one of the main thing is what is feed equal to mm per revolution, okay. So how to calculate feed? V equal to what is a F? F into N mm per minute, okay. See guys, sometimes why I am taking time is I don't want to tell you wrong thing, okay. So it may definitely confuse you, and also it may also confuse me myself also. That's why. Page number 13. Okay, then we we took a correct thing. Suppose if they have given feed mm per revolution like that, in orthogonal turning means you have to just be careful, okay. Okay, so what is an R? So R is chip thickness is 0.5, chip thickness is TC equal to 1.25. So 0.5 divided by 1.25 is equal to R, okay. So calculate and put it and we'll get the answer, okay. So you can just go for this one. You can see in orthogonal machining with the two, okay, orthogonal rake angle, okay. Okay, the minimum shear angle between okay, maximum divided by minimum. So okay, so R1 equal to 0.2 divided by 0.25. So this R1, R2 equal to 0.2 divided by 0.4 mm, okay. Just make sure this one, and I think so you can understand tan inverse sigma max equal to R1 cos of alpha divided by 1 minus R of sin. So just take 2 times and divide, that's it, okay. Just a basic thing, I think so you can understand, okay. So you can just go for this one. So you can see a bar of 70 mm diameter, okay, 70 mm diameter is cut orthogonally, is reduced to 2, okay, then this side 1 mm, this side 1 mm. So like this it will be. So depth of cut is 1 mm. Orthogonal, so orthogonal, okay. In case of length of chip is find the cutting ratio, they are asking the R, okay. length of chip LC equal to 68.9 mm. Oh, determine the shear angle if the rake angle, so alpha is given 10 degree. So we have to find R and as well as the shear angle. So what is R equal to T by TC, LC by L, VC by V equal to sin pi divided by cos of this one. Okay, this one not needed, but anyway, tan pi equal to R of cos alpha divided by 1 minus of R of sin alpha. So length of chip is given, so can we calculate this the other thing? Just think. So we can calculate the D. Okay, length of chip given, super. So depth of cut is, so for example just take this one too. Okay, for let us try T divided by TC equal to LC divided by L. Okay, equal to R. So just interclass, so just cross it. So this one will be T divided by LC equal to TC by L. Okay, so equal to R. Okay, but ratio will be same, but okay, let us try. So then 1 millimeter divided by 68.9 millimeter, so it looks a little bit contradictory. Okay, guys, what could be the answer? You just think. Good question in my point of view. Come on. Literally quite impressive, guys. See, simple calculation. Okay, pi into 69. So where is 69? Hey, where is this? Okay, so you can see what I just told, length of chip is 68.9. okay, and you can see length, it means length of the entire thing is how much? Only 69. So they just took in an average format. Okay, so it means where it is. Okay, so L will be how much? This one, how I need to say, means length of chip, and this one 2 pi r. Okay, so r is the radius. Okay, so in here what they have just did is, so this one they have just, you can see this is a mean length of chip, not a direct length of chip, mean length of the chip. Okay, so just take this average. So 70 plus of 68 divided by 2 is how much? So 3 1 5 35, this one 3 4, so it will be 69. So okay, so this is length, it means like this, like this it is been, that means suppose if you just make it a length, means 2 pi r will be. Okay, I think so, got the point, simple thing. Okay, so the length of the chip will be this thing, length of the entire cross section will be since it's been given diameter. Okay, we have to just convert to radius, that's it. So this one pi, it means diameter equal to 2 times of r, so r is equal to d by 2. So pi 2 pi r, it means d divided by 2. Okay, so pi into r is the length. Okay, so I think so you can understand, guys. So this is, what is this one? This is entirely radius. Okay, so calculate here, pi into radius is how much? 69 and equal to length. Okay, such a simple thing. Okay, then between 68.9 divided by 69. So calculate r and we can calculate each and everything. Okay, diameter 70 35 is the radius one. So next one 68 34 is the radius 2. Okay, See, so I got the point. Okay, this one is the radius of R1, this one is the radius of R2. Okay, 34, so this is 35. So we need to take here the mean length of the shape. So mean length, so 35 plus 34 divided by 2. Okay, and this is R. So 69 means 34.5 I think so, or 33.5 I think so. 33 or 34, 31, 34.5. So this is the, it means radius, mean radius. Okay, but length is 2 pi R. So what will be the thing? 2 into pi into R, 34.5. So pi into 69. That's it. Put and calculate. See, such a interesting question. So you can just go for this one. Orthogonal turning. Okay. Chip length. Okay, chip length is given LC 100. Uncut L is 250. Cutting velocity V 30 m per minute. So rake is 20. So simple. So R equal to LC by L. So next one, tan pi equal to R of sin alpha by cos alpha divided by minus R of sin alpha. Calculate and we will get the answer. Okay. So next you can see the following parameter determines the model of continuous chip or machine. Definitely rake angle of the thing should be okay, this I will just explain later on, so we'll just go for next thing. So during orthogonal cutting, an increasing cutting speed causes, so you can see cutting forces remain unaffected. Okay, so you can see this one in you can see the orthogonal turning. Okay, so orthogonal I think so you can see orthogonal turning process. So you can see what is thickness equal to F into sin 90. So T is this one 0.2, TC is 0.3. Okay, just calculate the that's it. So as I just told before, it's a simple thing, guys. Just a clear cut of mindset. That's it. Okay. So 1 second. Okay. Just 1 second. So the next thing, so guys, it is orthogonal cutting. Okay, orthogonal cutting, the depth of cut is halved. Okay. So let us try this one. So you can see in data as an IAS. Okay, depth of cut, okay, is halved. So if feed rate, okay, feed rate is doubled. Okay, 2 times of F. Okay. So what I just told to you, so thickness is equal to F into sin of lambda. So it's orthogonal cutting. Okay, not orthogonal turning or orthogonal just normal turning. So it is orthogonal cutting. So depth of cut is halved. Okay, depth of cut is halved means okay, it is thickness equal to 1 divided by 2, and feed rate doubled and the chip thickness ratio is unaffected. So R is same. Okay, then the actual chip thickness will be So it also must be halved. Okay, simple logic, just common sense. So for example, if r equal to what, t divided by tc. Okay, so they just told it means this is a certain, it means it becomes 1:1 ratio. So you can see what the condition is given, the depth of cut is half, so depth of cut is half, so 1/2. So suppose if we just take the chip thickness ratio as same, so what will be the thing? Okay, so it will definitely be, if it is 1 means what will be, it will, the ratio will be 1/2, so it should not be, so chip thickness ratio should also be 1/2, so then only ratio is called as 1. Okay, the main condition you can see chip thickness ratio is unaffected, so that's why it's been taken as half. Okay, okay, so this one you can see, this is cutting strain, it means cutting shear strain. Okay, so shear strain gamma equal to cot shear angle plus tan of shear angle minus of alpha. Okay, so this one not in a downward, so gamma equal to cot of plus of tan of shear angle minus of alpha. Okay, so you can see this one. So in this what they have just given, it has been IAS. Okay, orthogonal cutting, okay, rake angle. Okay, so they are asking what should shear plane. Okay, so gamma equal to cot of shear angle plus tan of shear angle minus of alpha. Oh, derive the formulate that is used to find. Okay, they are asking that to derive the shear plane angle and shear strain angles. Okay, so just now I will think first find shear angle, and after finding shear angle put here and we will calculate. That's it. Okay, next one you can see this one. So during orthogonal turning operation, hollow cylindrical pipe, it is found thickness of the chip is produced. TC is how much? 0.5. So lambda is the feed given to the 0 degree rake angle is okay. 0 degree. Okay, feed is 2.2 mm per revolution. Orthogonal turning, so orthogonal turning is T equal to F. Okay, T equal to 0.2 above. Yeah, shear strain date for this. Okay, so just a normal thing, first calculate the sequence alpha, after first calculate shear angle, after calculate shear angle, gamma equal to cot of shear angle minus tan of shear angle minus of alpha. That's it. Okay, put here and we can calculate. So you can, it means chip thickness ratio R is 0.3, so you can calculate tan pi equal to, it means the entire thing you can put and calculate. But in case of thick, suppose you are not able to find it, means just a simple thing, shear strain rate equal to 1 by chip thickness ratio 1 by R. Okay, that's it. It gives approximate value. Okay, so what the value will get? So okay, so the next thing you can see the minimum shear strain in orthogonal turning with the cutting. So you can see it is about, everything is taken about 45 degree. So while you just put 45 degree, we will get the recurrence. Okay, T is the thing. Okay, I think so, got the point. Okay, next one you can just go. So you can see a single point cutting tool with 12 degree rake angle. Okay, it's used to orthogonal measuring of between the shear plane of minimum possible condition. Okay, the shear plane angle for theoretical, they are asking the shear angle for minimum possible. So they given the 12 degree, so the shear plane angle for minimum. So okay, so first we need to calculate the minimum. Okay, so as I just told about, we need to calculate the shear angle. So this what how we can calculate. So you can see. So this is the formula. So shear angle equal to 45 degree plus of alpha divided by 2. 45 degree plus of alpha is how much? 12 divided by 2, so 51 degree. So in this 51, the shear rate will be so much minimum. Okay, I think so, got the point. So next thing you can see this one. So cutting speed is the velocity of the tool with respect to velocity of the workpiece. Okay, workpiece velocity. Okay, this is cutting speed. So actually velocity of the chip related to work, V is called as shear velocity. Okay, next one, the velocity of the chip relative to the tool, VC is called chip velocity. Okay, so that's it. So this is also one of the good thing you have to just keep in mind, this entire formula. So cutting velocity divided by cos of shear angle minus of orthogonal rectangle and non-linear rectangle. Chip velocity divided by sin of shear angle. Shear velocity divided by cos of rectangle. Okay, so you can see cutting tool rectangle given alpha, shear angle 45 degree, cutting velocity given. They are asking the velocity of the chip. Okay, the columns. Okay, so just to calculate, it means make sure V equal to cos minus alpha equal to VC divided by sin of this one. Okay, just V they have given cutting velocity, they are asking the chip velocity on chip velocity. So put here and we have calculate VC, that's it. Okay, so this one is here. So no need to confuse, just a simple thing. Okay, when we consider about this one, you can see let's see this one. So in orthogonal cutting, the cutting ratio is found to be 0.74. Just 1 second. Okay. So I think so this you can do, this one also you can do, and next one you can see about this one. In orthogonal cutting, the cutting ratio is found to be 0.5. Cutting ratio, so okay, cutting speed okay, depth of cut okay, so which also, so I think so you can use this one. So they have just given each and everything or VC of it, so maybe chip thickness, chip velocity and everything you can just calculate. Okay, so this one just it means division of the two things. Okay, that's it. Okay, not means not a bigger case scenario also. So this one you can see they asked only the chip velocity. Okay, that's it. So cutting speed and depth of cut is given, chip thickness given, so you can easily calculate the chip velocity. Okay, so this one you can do, and this one you can easily do it when they are asking the cutting velocity. So we go to pi dn, you can see pi dn, so this is revolution per minute, but we need revolution per second, so you can see meter per second, so convert to divided basically, that's it. Okay, okay, I think so you can understand. So guys, it's not a bigger thing and it's also not a small thing, just take it casual and make it, that's it. Okay, so you can see cutting, orthogonal turning. Okay, orthogonal turning. Okay, so they have just two questions, orthogonal turning operation. So chip thickness okay, the shear plane okay, you can calculate orthogonal turning operation, velocity carried out, cutting speed is this one, cutting tool angle is this one, the chip thickness. Okay, chip velocity I think so you can easily do it. Okay, we know the formula, that's it. And I think so you can see this one. So you can see here there are two type of things. Okay, you can see in this side, I think so you see this one. Okay, this is primary shear zone. Okay, but this side you can see this is secondary shear zone. So in this zone it means primary shear zone, metal flows like a fluid. Okay, in the primary shear zone, but you can see in the secondary shear zone it flows due to the friction. Okay, due to friction. Okay, primary shear zone and secondary shear zone, right? So tau equal to nu du upon dy. Okay, du upon dy equal to v of s divided by t of s equal will come. So gamma is d is gamma divided by dt. Okay, velocity of the s divided by thickness of the primary shear zone. Okay, that's it, ts. Okay, thickness of the shear zone can be taken as 1/10th of this one. Okay, maximum value is 25 micron, that's it. Okay, so they are asking the shear strain rate. Okay, this shear strain rate equal to velocity of chip divided by thickness of the primary shear zone. So 25 micron means 10 power minus 6. Okay, just put and we can calculate the VS is, I think so you would have known about the formula, by using this we can just calculate, that's it. So next thing, can see cause of chip formation. Generally in the ductile material shear yielding happens, and then in brittle material brittle fracture iron has been occurring. Okay, So mechanism of the chip formation in the ductile material. So you can see it is continuous chip, but in the brittle material it is not continuous. The crack propagation will occur and discontinuous chips will occur in the brittle material. So continuous chip and discontinuous chip, you can see discontinuous chip is not there, but continuous chips with the build-up. Okay, so build-up page is okay. So condition for forming discontinuous chips, you can see irregular section chip and work material brittle such as grey castain. Suppose work material is ductile, but hard and work hardenable. So okay, you can see copper and brass are ductile, but it doesn't flow because this is not okay. So when a material is work hardenable as well as hard, and you can say mild steel and alloy steel, so they go in a plastic and very hard, it can means it can go to discontinuous chip. Okay, feed is large, depth of cut is large, tool rake negative, cutting fluid happen and it can multi-point. Okay, which is the next one is plain milling of a mild steel produces okay, produces regular shaped discontinuous chip. Okay, continuous. So suppose build up pitch. So what is build up pitch? I'll just show you to. Have a clear look upon it. Will just okay, you can see now it means this is the tool. It is the tool is cutting the material. So you can see. So you can see after a certain amount of time, you can see now the tool is not cutting. The build-up which is cutting. Okay, here huge amount of stress concentration will occur. Okay, but over a certain period of time, you can see tower. Just 1 second, guys. So you can see now the tool has been cutting. So now the tool is not taking any kind of stress, but everything the build-up is taking. Okay. So see. Now will the cut be proper? No, the cut won't be proper. So you can see now here you can see now the tool itself, the deformation occurring. The tool itself not going in a proper way. So if this build-up edge comes and sticking to the tool, it is adhesion properties. Okay, so you can see sudden cutting is occurring. So irregular shapes, you can see it's not been straight, it is irregular. You can see here irregular. So sudden if this build-up edge become, it is broken, means this tip goes to broken. Okay, so that's why build-up edge is so much problem. You can see here huge amount of compression stress will be. Okay, you can see this is primary shear zone and this is secondary shear zone. Okay, so you can see here the entry in the secondary shear zone, the build-up edge is so much higher. Okay, I think so. Got the point. So that's the condition for this. Okay, condition for formation continuous chips without build-up edge, work material ductile and cutting velocity high, feed slow, rake angle positive and high, cutting fluid both cooling and lubricant. Okay, during machine excess material is removed in form of chip in and turning. Which one of the continuous grip bond chip in produced ductile material and as well as high cutting speed. So condition for forming continuous chip with the build-up edge. Okay, you can see cutting velocity medium. Okay, these are just the simple things. So core speed, low rake angle, low cutting speed and increase efficient cooling helps to produce continuous chip with the build-up edge in a rail metal. That's it. So I think so. Build-up edge. Okay, build-up edge formation. So in investing ductile material with the long chip tool contacts with lot of, I just told you now. You can see develops in a secondary Z formation zone under chip tool interface. Okay, so under such a high stress and temperature, two clean surface, strong bonding, so adhesion is so much higher, so little bit of welding will occur. So build-up edge formation, such bond will be encouraged and accelerated if the chip moves towards and mutual affinity. So exchanging of the, it means molecules will also occur in this. Okay, so you can see it grows like MPO and it destroys. So with the growth of build-up edge, the force also gradually increases due to wedging action. So will this form? So whenever the force exceeds the bond, so the build-up edge itself will be just broken. And just how it is formed is low cutting speed. Okay, contributes is kind of build-up edge, and in kind of non-metallic ceramics and all build up its own form. Okay, in negative rectangle build up its own form. Okay, so external effect of build up edge of poor surface finish, unfavorable change of rectangle, and power consumption so high, and definitely induce vibration. So build up edge protect cutting edge and tool life increases definitely, but sometimes it may also just deplete. So serrated chips. Okay, I'll just show you. Why my net is this much a problem? The soda phone is really irritating me. எங்கே வச்சாலும் நெட்டே வர மாட்டேங்கிறாடி. என்னடா டவர் வச்சுருப்பாங்க வோடஃபோன்காரங்க. ஐயோ டவரே வர மாட்டேங்குது பைத்தியம். ஸோ So you can see serrated. So you can see here you can see this one. So the chip is not in a regular format. It is zigzag like a wave format like it is there. Okay, I think so. You can see this one. So like this only serrated chips generally forms. I think so. You can see this one. Separately it has been formed in. Okay. So this is serrated chips. Okay, serrated chips are also called a segmented non-homogeneous chips or semi-condenser with low and high shear strain. Okay, shear strain. So material is low thermal conductivity and the strength that decreases sharply with the temperature, such as tight anim exhibit this kind of behavior. Okay. So chip breakers also we use. So chip breakers is called groove type, step type, and clamp type, and second is rake type. Okay, so that's it. Okay, so first half we just completed, and there is second half, and this one ended in second half. So this will be quite interesting thing. So after completing of this thing, we'll just go for tool wear. So this will be the third part. So mostly it may take it approximately 6 classes or 7 classes, I think so. So within next week, or today is Thursday. Today is Friday, so Saturday, and within next week I'll try to complete this entire thing. So okay guys, then I'll just see you in the next video. Take care, bye bye.